be off. Or they're 700 times, so it should be on. And then some of these, couple do some more over some, a couple of that, you know, that works. It's not gonna do that for, I'm just, oh. Or you can find on the button.
Then under should be. No, where is it over the one? I mean, why do you do? Everything divided by. Or.
Okay, so let's go about.
So that's 5, 8.
All right, everyone, so today we have Sanjoy there for the track. We did a second work. Oh, so let's set it up. Here we go.
Yeah.
Yeah. The preach or. Just to the laptop and then just write stuff on the board if needed. If the person is on. If you want to. Because it's not, there's Remember the light bulb, we can run out of power. Yes. So there's some people who are on Zoom. Yeah. That's why I know some people. And they can't see the board, but. This one is this, you guys are high schooler? Like what grade are we talking about? Going into the junior year, so just finishing 10th grade.
I finished 11th grade, so I'm going this evening.
Okay. Nice, and your interests are in like what, is this math? Everybody?
Yeah, that's basically
Oh, okay, nice. And which high schools do you guys go to?
the same as ours.
Ah, okay. Ooh, very good. I think it's in here.
Yes.
Also, it's the attention. You guys have first line?
Yeah.
And what about you guys?
I can invest in it.
Okay, in Carmel Valley?
I'm in Chicago, I live in so central.
Oh, so you're high school in Chicago? Yeah. Okay.
Can you check the You check this one really back. And so you guys are here until what time usually? 5 o'clock. Okay. Okay, so Sanjoy Dasgupta, who's the professor here in UCSD, will give a guest lecture today on nearest neighbor classification.
Hey, the people who are on Zoom, can you people hear me actually? Okay, thank you. Thank you for nodding. Okay, so I will talk a little bit about nearest neighbor classification, which is a simple form of machine learning. Okay, and I don't know what kind of background you guys have, so just ask questions at any time. Okay, this is meant to be 100% understandable. Okay, so if there's anything that doesn't make sense, go ahead and ask. So sort of an introduction to machine learning stuff, which maybe you've seen before. So the idea here is that we want to solve a particular problem. And the problem is that you're given a picture of somebody's handwritten digit, and you want the computer to just look at that picture and say what digit it is. Okay, so you want the computer to be able to look at this and say, oh, that's a 3. And here's some more examples. Like for that, it should say it's a 0, it should say it's a 1, a 2, and so on. Okay? And the question is, how do you do that? So this problem became very prominent in the 1980s because the Postal Service, so back then, people used to write a lot of letters, okay? And these things had the, at the end of the letter, you would have the zip code. And normally a human being would have to look at these zip codes. And it was, it's really a lot of drudgery and was very time consuming to route it. And said, okay, I think this zip code goes in that bin and so on. And so what the post office was very interested in, because there was increasing computerization, is that can we get a computer to do this? And what they found is using the technology at the time, they could certainly pull off the 5 digits, and they could also separate out the digits because there was a clear amount of space between them. But then they were left with this problem, where they had 5 of these guys, and the computer, they should somehow figure out which of these digits is correct. And so this was sort of a challenge at that time. So computer scientists were the best and said, this is easy. This is not going to be a problem. Obviously, we look at it, we at once know what digit it is, what are the rules that we're using? And so they said, okay, well, it's kind of obvious because a 0 just has a loop, and a 1 has just got a straight line, and a 4, that's, it's got these 3 lines. And so obviously the way to do it is to write a software, to write some computer program that takes the image and figures out how many loops there are. And then figures out how many lines there are and what's the orientation of these things. So if there's just one line and no loops, it's a 1. If there's just one loop and no lines, it's a 0. And if there's 2 loops on top of each other, it's an 8. So they got to work on that and they could just never get it to work. Okay. And there were lots of problems. So first of all, you have guys like this person who has not completed their loop on that. Okay. And this is just all sorts of things like this, just sloppy handwriting. Okay. And so this caused endless problems. Then you have like this person who likes to make a little knot in there too. And then all sorts of other flourishes. Some people like to have like a little candlestick, kind of like a 1. This just caused endless problems. So it was, first of all, hard to determine exactly how many lines and loops there were. And secondly, because there were so many ways to write each of these digits, it just led to endless rules. Because there wasn't just one way to write a 1. So you needed like 50 rules for all the different types of 1s you could have, or like 20 rules for all the different types of 0s. And the number of rules got just so large that the whole system became really brittle and it didn't work. Okay. And so this problem that initially they thought would be really, really easy, turned out to be a little bit more challenging than expected. So instead, they said, we are going to use the machine learning paradigm. And the machine learning paradigm is that, look, obviously there's some structure here. We just look at it, we can tell, it really stands out to us, the 0s, the 1s. But if we are trying to ourselves formalize what that structure is, or loops and lines and positions, it's very hard. Why don't we let the machine do it? Okay, whatever the structure is, let the machine figure it out. Okay. Now, are there any questions online? Is that, if you guys have questions, so no need to put it in the chat. You're welcome to just like speak it out, okay? Because that would probably be easier. And likewise, if you guys have any questions, just go ahead, okay? But I wanted to just sort of introduce the machine learning paradigm, which is that, look, there are patterns in data, there's structure in data, but often the structure is very hard for us to figure out. So let the machine figure it out. And what the machine needs to figure it out is just a big data set. And the post office is happy to provide that. Okay, so they said, you know what? Take this data set, it's got 60,000 pictures. And somebody sat down and labeled all of them. They said, oh, that's a 5, that's a 2, that's a 9, that's a 9, and so on. Okay, so somebody sat down, there was 60,000 pictures, and each of them had its corresponding label. And now the idea was to get the computer to figure it out. Okay, so they said, using these 60,000 pictures, figure out the patterns, develop a system, and then we've got this separate set of 10,000 test images. Whatever system you come up with, you can try it out on these test images, and that's how you'll know how good you are. Okay. Okay. So one particular way of doing this is called nearest neighbor classification. And what happens there is that if you get a new picture now, and you have to figure out which digit it is, you take the 60,000 that you have, and you just look at all of them, you compare them, it's like, does this look like that? Does this look like that? Does this look like that? And you just go through all 60,000 of them, and you say, which one is it closest to? Okay, and you say, you know what? It looks closest to this guy. And then you say, well, what was the label of that guy again? Oh, it's a 3. So we'll put 3. Okay, so that's the idea of nearest neighbor classification. It's very simple. There's no real learning going on. You're just memorizing everything. You just have a big table with all your 60,000 pictures and their labels, and you just find the closest one. And whatever its labeled was, you output that. Okay. Now, in terms of notation, I'm gonna call the images X superscript 1, X superscript 2, X superscript 3. And I'm gonna call that labeled Y superscript one. So this picture, this entire picture is X superscript one. And it's labeled Y superscript one is equal to one. Okay, so these labels are just numbers in the range 0 to 9, and these X's are pictures. And so this is going to be the nearest neighbor classification strategy, and it's a very simple classification method. Now, in order to realize this, we need to define a notion of similarity between the pictures. And that is a tricky business, because we have to figure out which one this is closest to, which one does this look most like, okay? And so we need a good way to measure the distance between two pictures. And the first question is, how do you even represent one of these pictures in the computer? So it turned out that in this case, these pictures are 28 pixels high and 28 pixels wide. And basically each pixel is 0 if it's black. So the value here is 0. And if it's fully white, the value is 255, and everything else is in between. So they're integers, and they kept it in that range because that's 8 bits. Okay, so they could store it nice and compactly. And so that's what these pictures look like. Okay, and so the main thing is every picture was the same size. Okay, and so now in order to apply machine learning, most methods, or a lot of methods, like the data to be in the form of vectors. And in this case, or just arrays of numbers, okay? And in this case, it's like a 2D array, you know? So what you do is you just stretch it out into a vector. So you say, okay, there are a total of 28 by 28, which is 784 positions, okay? And so we have a vector with 784 coordinates. And you start by copying down the first row, okay, which by the way is all zeros in this case. And then you copy down the second row and so on. And each row is 28 numbers, and all the way to the last row. And so you basically stretch the picture out into a long vector. And most of them are going to be zeros in this case, and there'll be like a few 200s in the middle somewhere and so on. And so that's how the pictures are represented now. And so what we'll say is that the data space now is 784 dimensional space. Okay, so R, so just like a real number, but 784 dimensions. So a vector of 784 entries. And the set of possible labels is 0, 1, 2, 3, all the way to 9. Okay, and so now what we want to do is we want to get a 784 dimensional point, and then we want to output what label we think it is. Okay, so now we know how the pictures are represented. They're just vectors of a fixed size of 784 dimensions. But now we need a distance function between two vectors. Okay, and so the first thing is, hey, why not just use Euclidean distance? Okay, now you guys probably know this formula since it sounds like you all are pretty interested in that. So what is the distance between these things? Who can give me the number? No, well, what is it for these two? What's the distance between 13? Okay, square root of 13. Good. Because this leg is if I come, this is a 2, right? And then this one is 3, and then there's a right angle, so it's like square root of 2 squared plus 3 squared, so square root of 13. So excellent. Square root of 13, right? And this is physical distance. So we like this distance because for us, this is the most intuitive distance. If we take out a ruler and measure this, it would be, the ruler would say square root of 13, okay? So that's very intuitive, right? So that's our two-dimensional notion of distance. It's a distance between 2D vectors. But now we can do the same thing in higher dimension, okay? So let's say a 3D example. So let's say we just had 2 points in space, okay? And we wanted to measure the distance between them. Again, physical distance, like if I took out a tape measure and measured it, right? So now we would represent the points by 3 numbers. Like let's say that this would be the point 0, 1, 6. Okay. So this is the point 0, 1, 6. And now let's say this is the x-axis. So this is 1, and this is the y-axis. So that's maybe 4, and then this is the z-axis out here. Okay, so that's what that means. So we have some other point, which is maybe 2, 5, 9. Okay, so we'll call this x, and we'll call this z. And now when we want to talk about the distance between them, we'll write it like this. We put like the double bars, so like the length of the vector, right? And so what do you think would be now? So we'll do again the square root. And now we, for each coordinate, we look at the difference along that coordinate. So in this case, there's a 2. What's the next one?
4,
And then,
3,
okay, so we take the square root of,
2 squared plus 4 squared plus 3 squared. 28 squared plus
square root of what?
20.
Okay, that's your word for it. Any objections to this? Okay, this is probably correct then. So that's how we would do distance in 3D. Okay, so we have 3D points. And we need that a lot. We often need to measure the distance between 3D points. Now, in our case, the points are not 2D or 3D, they're 784 dimensions, but still it's the same formula. Okay, now in this case, you can't actually measure the distance. Okay, because once you go beyond 3 dimensions, how do you actually measure stuff? But still, you can write down the formula, and that's what we do. Okay. So now we're gonna have one picture, let's call it X. And it's just gonna be an array with like all these numbers. So let's say X1, X2, X3. This is the top row of the image, all the way to X784, which is the very bottom of the image, okay? And then we have another image, Z, which we've again stretched out into a vector, Z1, Z2, Z3, all the way to Z784. And now we want a notion of distance between them. So it's just the square root of the distance along the first coordinate, the square distance on the second coordinate, all the way to the very last coordinate. No problem, right? And so now we have a distance between points. So how do you think we could compute this? If I gave you like these two arrays, how would you compute that distance? What do you think it would look like? If you were to program that?
Probably use it for loop or some sort of loop, and then you iterate through each one.
Yeah. Like, I don't know if you guys are familiar with computer program, but if you wanted to program this, you would have a for loop. Like for I equals 1 to 784, x sub I minus z sub I squared. And then at the bottom of the loop, you take the square root of the whole thing. And that would be the distance. Great. So that's how we're going to compute distances between pictures. This is one picture, that's another picture. And to compute the distance between pictures, we're going to use this formula. Okay. Okay, so now we get a test image. And now the image for us is a 784 dimensional vector. And this is a 784 dimensional vector, and this is a 784 dimensional vector. And in fact, this entire data set, we're just going to store it in a massive matrix with 60,000 rows and 784 columns. Where this is the very first day, this is the very first picture. Okay, so this is the first picture over here, that's the first row. And the second picture is the second row over here. Okay, so we have 60,000 rows. And now this thing is also a 784 dimensional vector. So we go and we compare it to this first one. We compute the distance between them. That's a for loop. And we get back a number, like 23.9. And then we take it and compute the distance of the second guy, and we get another number, 48.2. And then we compute the distance of the third guy, and we get another number, 33.2, and so on, right? And so we get 60,000 numbers in this way. And then we said, which was the smallest one? And it just turns out that the smallest one happens to be that. Maybe this guy over here, okay? And then we look at the corresponding labels, because we also have their labels, 1, 4, 1, 0, 1, 1, 1. We just look at its label and we spit it out, okay? So how long do you think it takes?
A few seconds, but
Yeah, Yeah, so it really depends on the computer you're using, right? If you're using a super duper fast computer, maybe no time at all. Using my computer, it's gonna take a while, okay? So because of that, it's like your computer, my computer. Let's just think about the running time slightly differently, right? Let's say that we think of the dimension of the data as being 784. So it's a 784 dimensional vector. And let's say we think of the number of points as being 60,000. So in order to compute the distance between 2 points, which of these matters, the D or the N? D. Because you're kind of going through the dimensions one at a time, right? So the running time is basically proportional to D to compute one distance. And how many distances do we need to compute?
60,000.
60,000 or N. So the total time is going to be proportional to N times D. Does that make sense? So the time is, we write it as O of N times D. Because the O means there's some constant in front of it, that is determined by whose computer you're using, okay? Using mine, the constant in front of it is huge. Using your computer, very small constant in front. Okay, so that's the big O. But basically, the dependence on the running time is basically N times 2, which means it kind of takes a long time. But let's see how it actually works. Okay, let's see whether this is actually any good. Does it do a good job at classification? So the main question is, how accurate is this model? Okay. Okay. So first of all, how accurate is it on the 60,000 points that we started? Okay, so we had these 60,000 points. Suppose I actually try it out on this point. Is it gonna get it right or wrong? Right? Why is it guaranteed to get that right?
Because the distance would be 0.
Distance was 0, but could the distance be less than 0 for one of the other points?
No, because that's impossible.
The formula doesn't let you go below 0, right? So this is the closest one. Now, unless there's another one that's identical that has a different label, which is not gonna happen. The nearest neighbor of this is itself. And so every single one of these points, it gets correct guaranteed. So we say 0 training error, okay? Does that mean we have a perfect classifier? No. It could be really bad on everything else, okay? So when they talk about training error, it means how well are you doing on the training set? And in this case, guaranteed 100% performance on the training set could be simply atrocious on the next, on the other numbers that you get on these envelopes that the post office gets, right? So training error means very little. In this case, you're guaranteed 0 training error. Okay. That's why the post office gave these other 10,000 pictures, okay? Because they knew this. This is, you could get 0 error on the training set, no problem at all, okay? So we are gonna give you a separate set of 10,000 pictures of these handwritten digits and see how you do on those kinds. Okay? And that's what we call the test error, the error of the test error. So here's a question for you guys, since you guys are fond of math. Suppose the way the classifier works is this. They said, you know what? You've given me the 60,000 points. I don't even care. When you give me a new picture, I'm just going to close my eyes and pick a digit at random. What do you think is the error rate of that classifier? Sorry?
1/10.
1/10 is the chance of it being correct.
So 90%.
So the chance of it being wrong is 0.9. Okay? And does it matter what the digit it is? What digit it is? It doesn't matter what, right? If you're picking at random, there's a 90% chance of being wrong. Because whatever the label might be, the chance that you happen to pick that one is 1/10. So a random classifier would get 90% error. And we want to do better than that. We certainly want to be better than something that's closing its eyes and picking at random, right? So you can think of that as sort of a baseline. We want to do better than random. Does that make sense? Okay. So how well does this do? 3.09? Not too shabby. Okay. So how many points did it get wrong? The test there.
Oh, sorry. Yeah.
Sorry? 309. So there were 10,000 test points, 10,000 pictures. He got 309 of the pictures wrong. Okay. And so the test error was 3.09%. And that's pretty decent for something so simple. Okay. So that's good. Now we have a new baseline. Okay. So we said, okay, before we had anything, our baseline was 90%. That was the one thing we knew we could do. Okay. Now we can do 3.09%. That's way better. So now what we should do though, is we should see, well, these 309 that it got wrong, why is it getting them wrong? Like, what are some examples? And so I'll show you some examples of the ones it got wrong. I just picked five of them at random, okay? So this was the query, this was the actual image in the test set, and this was its nearest neighbor. What do you think the correct label is?
6.
Yeah, so that probably is 6, who knows, okay? And this was the nearest neighbor. Why is this the nearest neighbor?
It kind of looks like that. 6.
Yeah, I mean, if you think of like these two images and you superimpose the pixels, there's a lot of overlap, you know, it's got kind of like a lot of those, because, you know, these pictures are mostly blank, right? And the region where this actually has something, there's a lot of overlap. And so this was the nearest neighbor. And so it thought it was a 4. Okay, here's another one. What do you think is the correct digit here?
Kind of looks like the partial derivative sign.
Yeah, so it was like either a 2 or a partial derivative, right? And it thought it was a 0. So it was like, you know, so these are examples of that. And to be honest, you know, these are not so bad. If people are writing like this, they do not deserve their mail to go to the right place, frankly, you know? So these are the kind of mistakes that it was making. And so the question is now, as usual, can you do better? Okay, and so we're already seeing 2 axes along which we can potentially do better. First, we would like the performance, we would like the number of errors to be lower, you know, even on these, you know, we want to get some of these right. Like this one we should probably have got. This is a pretty legitimate 8, you know, and this, I would argue that even this is okay, you know, so we should have got those right, okay? And the next thing is that the whole thing seems a little bit slow, because to classify one new picture, you have to look at 60,000 pictures and do like the 784 dimensional distance calculation. It's a bit of a drag, you know, and so if there were a way to speed that up, that would be good. And so these are 2 dimensions along which we would like to improve. And a lot of people have spent time thinking about these. Okay. Okay, so any questions so far? Yeah.
I've seen someone use like a neural network approach to kind of classify this. So how does the error rate of the nearest neighbor approach compare to the neural network approach?
Yeah, so the nearest neighbor approach was one of the very first that was tried. And this was probably in the early 90s. And also in the early 90s, people tried a neural net approach. And it was a French guy who did it, this guy called Yann Lequin, and he called it Le Net, because, so he tried this neural net. It was very famous at the time, okay? Everybody was like, wow, Le Net. And Le Net had the best performance on this data set. Instead of 3.09, it was 2 point something. Okay, so it was a little bit better. And then people tried to improve. And nowadays, this data set would be considered trivial, because we're working on much harder problems. Okay, so stuff like this, I mean, forget about it. Now you can hope to classify not just the digits, but all the characters, and not just in English, but like in every language ever known, and hope to get like performance better than, you know, 1%. Okay, so the bar has risen a lot recently, but for a long time, this was a benchmark that people were trying to do really well on. And it helped explore a lot of ideas for building better classification systems. So a lot of systems sort of cut their teeth on this particular data set. Yeah, so at the time, there was a neural net method, and it did pretty well. Anything else? Okay. So there are two easy ways to improve this, okay? The first is that, you know what, instead of just looking for the very closest picture, look at the three closest and take the majority vote. Okay? And that helps a little bit. So in this case, if you look at just the very closest ones, you go to 360,000 and you look at the smallest distance, that's the closest neighbor. Or you can look at the three closest and take the majority of them. If like two of them think it's a 6 and one of them thinks it's an 8, you say 6, okay? And that is a little bit better. It gets only 294. If you take the 5 closest, then it's worse, okay? So this helps a tiny little bit in this case. In other cases where you use nearest neighbor, this helps a huge amount, okay? So in this case, it's not doing too much, okay? But this is called K nearest neighbors. Second thing that helped a lot in this case, and that in fact always helps, is to use a better distance function. Now, this is a little weird because, I mean, when we say distance, the first thing that comes to mind is literally physical distance. So how could we possibly write down a different distance function? Okay, or like, what would that even mean? Okay. But, so just to explain why Euclidean distance is really bad, actually, for this, so that's our generalization distance, we're just gonna call Euclidean distance, even if it's in higher dimension, okay? So look at these two pictures. They're exactly the same picture, except that we just taken the one and kind of scrolled it a little bit to the right, but it's literally identical, okay? But the Euclidean distance between these vectors is substantial, okay? Because if you think of them as a vector, then the places where these things are completely disjoint from the places where these are. So the positions that are active in one are completely disjoint from the other. And so there's actually a substantial difference between them, even though it's exactly the same picture. So that's a sign that something's wrong. Okay, that's a sign that if we actually want to measure the distance between pictures, this might not be the right distance function to use. And so people spent a lot of time mulling over this, okay? And the community that was particularly interested in this was the computer vision community. So computer vision are the people who are interested in processing pictures. And they loved nearest neighbor, and that's been their go-to method for a long time. And they realized that they needed different distance functions. So what they said is that can we come up with a distance function that is invariant to small translations and rotations? So if you take this and you translate a little bit and you rotate it a little bit, can we somehow come up with some distance function that can deal with that? And then another one said, can we do something that's invariant to small deformations? So let's say they said you take this and just kind of deform it a little bit, you know, just sort of change the curve of the one. And they tried to cook up stuff like this. And these were huge results of the 90s, okay? And it turned out that if you do this one, the tangent distance, the error rate drops from 3.09 to 1.1. And if you do this one, which is called shape context distance, the one with the deformations, then it drops down to 0.63. Okay. And these are much more complicated distance functions to compute. Okay. Just to give you an idea, I mean, we thought Euclidean distance was bad because in Euclidean distance, you look at the corresponding positions and you look at the difference between them and you square them and then you add them up. And that seems like quite a lot of computation because you're looking at all these positions, 784 positions. But for something like shape context, the first thing you do is to identify some hotspots on the image. In this case, for example, this is a hotspot that's easy to pick up. This is a hotspot that's easy to pick up. And some stuff along the edges. And then you find the hotspots in the two images, and you try to you try to find the best mapping between the hotspots. And this corresponds to some very gnarly matching problem, okay? And just computing the distance takes a long time. But that's what was needed. And the fact that they were able to demonstrate this superior performance was just evidence that just picking the right distance function makes all the difference. Okay, and so that makes a big difference in nearest neighbor classification. So any questions about that? Okay. So the last thing I wanted to talk about So we have like a few more minutes. Okay, good. So the last thing I wanted to talk about was, so what we've seen over here is that we took these pictures and we made them into vectors of fixed size. And that was the first thing we did, okay? And in fact, a lot of machine learning requires the data to be vectors of fixed size, okay? And that's a little bit puzzling because so much of the data that we have don't seem like they would be fixed size. Like if you look at images, for example, in this case, the images were all 28 by 28. But if you look at regular pictures, they're all different sizes. You know, some are big, some are small. How do we make them all the same size? Or sound, somebody says something. How is that even a vector? You know, because it's just a speech signal. Or text, somebody writes down a sentence. How do we make that into a vector? Okay. And so because we spend so much time processing these kinds of data, people have come up with really good ways to convert them into vectors. And so I just wanted to give you a couple of examples of this, okay? And so how much time do we normally have until when? Okay. So let's talk about sound, for example. So sound, like, so I'm talking to you guys, right? And so there is this sound wave that's propagating through the air, and then it gets to your ear. And in your ear, there is like a super thin diaphragm that's wiggling, okay, in response to these changes in air pressure. And you can think of the sound signal as literally the displacement of that diaphragm. So like some super thin diaphragm, think of it horizontally, think of it wiggling, okay? And so that's the sound signal. So something like this. It's literally the displacement of that diaphragm. Okay. So as time goes on, this is the displacement. And this just goes on and on. Okay, I'm talking for like 50 minutes or an hour, and this is like an endless sound signal. Okay, so the question is, how on earth do you make this thing into a vector? Okay, and so the way we do it is, or the way that it's often done, is that you say, well, we're just going to look at little chunks of it at a time. Okay, so for example, let's look at a chunk whose duration is 25 milliseconds. Okay, and then in that chunk, you still have a continuous signal, right, within the 25 milliseconds. But what we're going to do is we're going to take it and multiply it by something that looks completely flat. If we multiply by something flat, we're basically adding up all the values. It's like integrated. And then we multiply by something that looks like a triangle. And then we multiply by one of these guys. And this is called filtering. It's just like taking different dot products of the sound with like different shapes, like predefined shapes. And in this way, if we multiplied it by these three things, this would give us a single number, and a single number. And so this entire window would be boiled down to three numbers. Now, three is not enough. There's actually a lot more. And this whole area is called Fourier analysis. Okay. And so you have all these like different shapes that you use. Okay. And maybe you have 40, maybe you have 100. And in that way, this continuous signal inside a small window is mapped to a bunch of numbers. And so great, the sound is being made into a vector of fixed size. Okay. And so then we can classify the sound. Like at like 25 milliseconds, you can't classify the entire sentence, but you can classify the particular phoneme, which is like the subword unit. Like, you know, if you say light, it's le, I, you know, it's like, so the le sound or the I sound, that just that subword unit, which is called a phoneme, there's only like 40 of them actually in the English language. And in English, there's only about 40 phonemes, and you can classify them in this amount of time. Okay, that's a reasonable amount of time to classify them. And so you can find these subword units and then you kind of string them together and so on. But this is a way where even something like sound can be made into vectors. Okay, does that make sense? But now let's talk about text, okay? How do we make a document into a vector of fixed size? Okay, so we have some document like this. This is I think this is the Dickens, like A Tale of Two Cities or something like that. So you have a document, right? And you want to make it into a fixed length vector. And there are many ways of doing this. And over time, people have gotten better and better at this, okay? So let's first talk about a really primitive way and then like a slightly more modern way of doing it. So the really old school way of doing this was to say that what we're going to do is we're going to start by picking a vocabulary of a certain size. Like let's say you pick the 50,000 most common English words, okay? So you take an English dictionary and let's say you have a dictionary of just 50,000 words, you say those are the words I'm going to use. Okay, so let's call that B. Vocab of 50,000 words. Now you create a 50,000 dimensional vector with an entry for each of those words. Okay, so if the first word is despair in your vocabulary, the first entry in the vector corresponds to that word. The second entry in the vector corresponds to the second word. And what you do is you go through the document and you just count how many times the word occurs in the document. So you say, okay, word number one in my vocabulary is despair. How many times does it occur? And it's like, okay, we got just one occurrence. So we stick a one in there. Evil, how many times do we have evil? We got evil over here. And maybe there's another evil somewhere. Okay. That should just have been a one. But let's say there were two, then this would be two. So, right? And so you basically summarize the document by just a bunch of word counts. Okay, you've got your vocabulary, how many times did each of those words occur? And now each document has become simply a 50,000 dimensional vector. Right? So nice and simple. It's become a vector, and now you can use stuff like nearest neighbor search on it. It's a pity the running time is n times d, because now d is 50,000. Okay, but you can still use it. Okay. So this is how people used to do it, but there are some problems with it. Okay. And the problem is that suppose, so here we have an entry for happiness. So you can imagine there's an entry for happy, there's an entry for sad, but there's also an entry for content. There's another entry for pleased. And I mean, happy, content, pleased, these are basically the same word, but they all have different entries. And so it creates distance between these documents where none should exist. Okay? Because separate coordinates are used for synonyms, that's problematic. Okay? It's artificially creating differences between these documents that have these words and that might mean exactly the same thing. So that's always been considered a big problem with bag of words. And so nowadays, what people want to do is to do something different. Each word is now represented as a vector. Okay? So for example, there will be a vector for the word happy. And these vectors lie in 300 dimensional space, for example. Okay. And there'll be another vector for the word sad. But if you look at the vectors for words that are similar to happy, they'll be very close to the vector for happy. So what's a word that's like happy, would you say?
Joy.
Right. Okay, good. So the word for joyous would be right here. And what's a word that's like sad? Miserable? Yeah, miserable. So this is pretty cool. Each word is a vector, okay? And that's how we're going to represent documents, okay? Yeah.
How would you represent a word as a vector?
Oh, yeah, so how do you even find these vectors, right? But yeah, so we'll talk about that. But assuming we could do that, let's say we had this big table where for each of the 50,000 words in English, we have the 300 dimensional vector for it, okay? That would be great, because then in order to say represent a sentence, we could just add up all the vectors for the words in it, or something like that, okay? Or we could somehow like string them together in some way, okay? Um, okay, so here's a question on Zoom. What about words that have different meanings based off of context? Okay, so the question is that let's say that we have a word like some words have different meanings based on the context. Okay, so for example, chip could be potato chip. It could be chip on your shoulder. It could be computer chip. Chip off the old block. I don't know if they're now. Okay, so there are lots of different meanings, right? Depending on the context, right? And there are several examples like this. So depending on the context, the different meanings. And so the question is, what about this? What about chip? Okay. And that's a good question. So whoever posed that question, very good question. Yeah, I'm not sure exactly what happens with that. Okay, what you would expect is that, or what you would hope, is that in the 300-dimensional representation, there are different subspaces that correspond to different meanings, something like that. Okay, but what ends up happening nowadays is that you start with the default vectors in a sentence. So let's say you have a sentence. You take all the words and you get a 300-dimensional vector for each, okay? And so now these word vectors are relatively new, let's say 15 years, it started about 15 years ago. Initially, what you would do is you would just add up the vectors in the sentence. And so the whole sentence would be, say, 300-dimensional. Now what you do is you do exactly what the person who asked the question brought up, which is that now you actually adjust the word vectors based on the context in which it actually appears. So you look at the interactions between words and you tweak those vectors a little bit, and then you add them, you know, so. Yeah, so that's actually a great question. Okay, so this vector representation is a way of actually getting at the meanings of words, okay? Where vectors that represent vectors for similar words have are actually very close together in the sense that their dot product is very high, or we can think of their distance as being small, something like that. There are standard notions of distance. So how do we come up with these vectors? And the idea is, so there's this whole idea, which is you shall know a word by the company it keeps. And what that says is that you can learn a lot about the meaning of a word by simply the context in which it appears. You know, if I say, I drink a something every morning, just whatever that something is, just from the context, you can tell a lot about what it is, right? I drink a something in the morning. You immediately know it's going to be a beverage. Okay, stuff like that. Okay, immediately it tells you a lot about the semantics of the word, just knowing the context in which it appears. And so the way we do this is that we just get a humongous corpus of English documents, like all of English literature, for example. And for each word, like, you know, so you pick any word like happy or whatever, and you look at all the context in which it appears, like 3 words before and 3 words after. Okay. And based on this, you come up with a vector that sort of summarizes those contexts. Okay. And so just like the easiest way to do this is that for each of the words, so for each of the V words, actually, let's do it like this. For each of the V, we could do a V by V matrix where for each word and for each other word, you say, how often does this word appear in the context of this guy? Okay. And now you can represent this word just like this vector. So you represent the word just by counts of how often each of the other words occurred in its context. Easy. So you have 50,000 words. For each of them, you have a 50,000 dimensional vector. And it's like, how many times does despair occur right next to this word? How many times does evil occur right next to this word, and so on, okay? And now you've converted words to vectors, and unfortunately it's 50,000 dimensional, but there are all sorts of ways to just push that down to like 300 dimensions, okay? And so that's a very primitive way of creating these word vectors. And it's a way in which we can convert text into vector format. And so then you can ask questions like, which word vector is closest to that of Africa? And you might get, for example, Asia. You can ask, you can even use it to solve analogy problems. Like king is to queen as man is to what? And so what you say is that, look at the vector for king and the vector for queen and the vector for man. The analogy is king is to queen as man is to something. Well, we might expect it to the corresponding vectors to correspond to this algebraic relationship. And so now we know the vector for king, we know the vector for queen, we know the vector for man. So we just solve for this, we get some 300-dimensional vector. It doesn't correspond to exactly to some word, but we look at its nearest neighbor, the nearest word to it. And sure enough, it turns out to be one. Okay, and so it actually works for analogy problems like this. So yeah, you just write out the equation like this and then you use the nearest neighbor. Okay, so that's all I was going to talk about. So nearest neighbor and then some of these embeddings. Okay, so any questions for me before you guys take off? Yeah.
When you think about the sound, and how you like represent phonemes as like vectors, what if you're trying to train a model, are you training it with different phonemes, like repetitions of those, or are they words? And does it like classify it by, like if you give it like a sentence, a spoken sentence, and ask it to identify it, is it gonna look for words or like specific words?
Yeah, so the answer completely changed in 2016. Okay, so what the answer used to be was that people used to do exactly what I was showing in that picture, where the sound is broken down into little windows, and then you have phonemes, and then you know which phoneme is likely to come after which, and which words are made up of which phonemes. It was so heavily based in linguistics and phonetics and so on. Beautiful stuff, and that worked well. But it turns out that starting in 2016, people introduced for the first time this thing that was just a huge revolution called WaveNet. And this completely bypassed any of these fancy filters or anything. It just literally took the raw speech signal, sampled at a certain frequency. So, it's continuous, but you can just sample it, say, maybe 20,000 times per second, okay? And just return the number, so 20,000 numbers per second. And just directly from that raw speech signal, they sort of went to the sentence. Okay, and for the first time they were able to do that. It was sort of, it was really quite spectacular. And it required huge amounts of data and computation. But it sidestepped the need to go beyond things like phonemes as intermediaries.
So like pre-2016, if you like put down like Google Assistant or something and asked it something, would it like the like sentence that pops up and whatever query it responds to, was it using the phoneme method before and it changed, or like is that like a different thing altogether? Like how?
So I don't even know when those things were first introduced. The Google Assistant and so on that are actually pretty commonplace now. For the most part, these have gotten good recently. Yeah. For the longest time, I used to try to use these state-of-the-art speech recognition systems, and for the longest time, I never understood a word I was saying. So it's been recent, and so I don't know if they actually had these before WaveNet. Yeah.
These and
All on and that's that's where something where one healthy for I think one adding to the and I think that you be yeah by adding each and the elements with more efficient that would be more efficient. So yeah, that would be does the efficiency based on the whole fund and operating?
of the larger than property.
Is
So-
it based on, could be from from theory and then how you can. Affect
So what we said is that the nearest neighbor, if you do, if you try to nearest neighbor, it looks like it's like n times d to classify it. But it turns out that there are much cleverer ways of doing it that are closer that instead of n gets you something much smaller. Sometimes people like log. Okay, you know, so in order to find the closest, like, let's say you just have a bunch of numbers and you want to find the closest number in a set of n numbers, what you would actually do is just to sort the numbers, okay? And then when you give a new number, you want to find the closest number, you use binary search, which is just log it, much faster than comparing to every single number. So just like that, there are ways where even in higher dimension, you can hope to do nearest neighbor search in time that looks more like that is proportional to log n sometimes. That's right.
question. If not, let's give Right, so today's session and see everyone today. We have another game wrapping up. Alright, so make sure you do your problem test. Okay. Let's see, I think you know. Actually, yeah.